back to the channel and to the series. So in this video lecture we'll be learning about tree traversals. Like we learned about depth first search strategy. In this video lecture we'll see the breadth first search strategy, which is also a tree traversal algorithm and a non-recursive one. Okay, so as we all know that DFS is a recursive tree traversal algorithm, but this one, this BFS, we call it BFS. Okay, so again used for tree traversal. So we have a tree with some nodes like this: 0, 1, 2, 3, 4. Why do we call it breadth first search? Because we traverse the tree in the level wise fashion. So first we'll traverse all of the nodes at this level. So at this level we have only one node, which is 0. Now we move to the next level, which is this one, or let's call it level 1. So this is level 0, this is level 1. Here we have nodes 1 and 2. So now we traverse 1 and 2. Now we move to the next level, this one. Here this is the level number 2. Here we have nodes 3 and 4. So we traverse these nodes 3 and 4. So this is the BFS traversal for this tree, rooted at node number 0 with 5 nodes numbered from 0 to 4. How do we perform this traversal? So to perform this traversal, we basically use a queue data structure. Okay, so we have got a queue initially. So what is a queue? We know that queue is basically first in, last out. Sorry, first in, first out, first in, first out following data structure. So any element which I am pushing. So if I am pushing an element here, this one, element number 1, this element will be popped out. So I am pushing it from this end and I am popping it from this end. Fine. So you get it. The later an element I am pushing, the later it will be popped out. Okay, that's the idea. Fine. So first of all, in this queue, you'll understand why do we use queue to perform BFS traversal. So to perform the BFS traversal, I'm using a queue data structure. So take a queue. So this is the front of the queue. This is the back of the queue. I'm pushing it from the back. I'm pushing elements from the back and I am popping them from the front. Okay, so it is open from both of the ends. So first let's push 0. Push 0. Also mark this node number 0 as visited. That means we have visited this node. So since this is visited, we mark the node number 0 to be visited. So we take a visited array. This is a visited array. 0, 1, 2, 3, 4. So mark 0 as visited. Okay, and print this one. So pop this from the queue and print it. Now traverse its child nodes. Basically the nodes connecting node number 0, the node which I have popped recently, which have not been visited. They are the child nodes. They are node number 1 and node number 2. So push these nodes into the queue as well. Push node number 1, push node number 2. So this is out. Node number 0 is out. Now mark 1 and 2 visited as well. Now in the next iteration, pop this node 1. Pop this node once and print it. Now push the child nodes for node number 1. What are the child nodes which are not visited? Node number 3 and node number 4. So push node number 3 here and push node number 3, push node number 4. Okay, now pop this node number 2 from the queue and print it. Now, do we have any child for node number 2 which is unvisited? No. All of the child nodes for node number 2 are node number 2 do not have any child node. It only have one node which is connected to it, which is node number 0, which is already visited. So 2 is out. Now pop node number 3. Do we have any child node for node number 3? No. So print it. Now pop node number 4. Do we have any child node for node 4? No. So just print it. Now we have printed the nodes in the order, in the level order. So first of all, the nodes on level number 0 are printed, that is node number 0. Then on level number 1 is printed, which is 1 and 2. Then on level number 2 are printed, that is 3 and 4. Fine. So they are printed like this: 0, then 1, 2, then 3, 4. That's the idea of BFS, or breadth first search traversal. So you see what are the elements which we are using here? We are using a queue, okay, and we are using a visited array, a boolean array. Why we are using a boolean array? We are using a boolean array so that we do not revisit a node which is connected to any particular node. So let's say we have node number 1 here. We have visited node number 0, then we have moved to node number 1. We do not revisit node number 1. That's why we use this visited array. If we had a directed graph, if we had a graph like this, 0, then we have a directed node, then we have a directed edge towards 1, we have a directed edge towards 2, like this. In this type of case, we do not use this visited array. Only in case of undirected edges, we have to use this visited array. And why we are using this queue? Just to push the nodes in the order, in the level order. Like I pushed node number 0 first, then I popped it first. Then I pushed node number 1 first, then 2, which are the child nodes of node number 0. So 1, 2, and they will be popped out in the same order: 1, 2 first. Then I have pushed 3, 4, then will be popped 3, 4 in the order I am pushing. That's why it is called a breadth first search traversal. Okay. So after visiting node number 0, I will visit all of the child node for this node, then I will visit all of the child node for this node. Fine. So I am just pushing the nodes, and then I am printing the nodes which were pushed before the nodes I am pushing right now. Okay. So 3, 4 were pushed after node 1 and 2. So that's why 1 and 2 are printed before 3 and 4. That's the idea. The first we push a node, the first it will be printed. And let's just jump to the code implementation part. So let's say we return a vector BFS. We have a tree which has n nodes. Okay. Now use a queue. Let's call it queue, and a visited array of same size n, where n represent the number of nodes that we have. So in the queue, push the source node, and I'm pushing the source node, which is the node number 0, or the root node. Now run the BFS search, that is iterate till this queue is not empty, till this queue is not empty, and then just pop the top element. Okay. And also mark 0 number, node number 0 as true, or 1 as visited. Okay. This is visited. Now pop the node, the front node from the queue dot front, print it, okay. Then after that, mark the iterate over the child nodes for the current node. So iterate over the child nodes. If you find any child node which is not visited, so if any child node is not visited, if it is false, Then push this child node into the queue. Okay, so you get it. Now also, whenever you are like, you have to pop the node which you are pulling out, so pop the node as well. And as soon as you push a child into the queue, you mark it as visited. In the visited array, mark this child as true or visited. Fine. So that's all. That's all. That's how the BFS works. Fine. Just a while loop, and let's just jump to the code implementation part. So here you can see that we have adjacency list prepared from the given set of edges, and this is our visited array, and here I am calling this BFS function where I'm passing the tree as well as the visited array. So let's create a queue of type integers, push the node number 0, which is the root node, into the queue, and print this node number 0 here. Also mark this node number 0 to be visited, and iterate till this queue is not empty. Pop the front node from the queue, print it, queue dot pop. Now print it, print, then iterate over the child nodes, and if you find a child node which is unvisited, push it into the queue and mark it as visited. Okay, then that's all. Let's just run it. So this is the input and the output is this one. Okay, let's just see. 0 1 2 3 4. So we have taken the same input. We have an edge between 0 1 0 2 1 3 1 4. So this example 0 1 0 2 1 3 1 4, and the BFS traversal would be 0 1 2 3 4, obviously, which is the case here. Okay, so that's how BFS works. It's a level order traversal thing, and we traverse the nodes according to the level. So we traverse the entire level, then we move to the next level, then we move to the next level, and so on. Fine. So the time complexity for this BFS traversal is big of n, because we are traversing over all the nodes. The space complexity is also big of n, because I'm using a queue data structure, and in the worst case the queue may store all of the nodes, right? So that's all. That's all for this video. If you like the video, then hit the like button and make sure to subscribe to the channel, and I will be posting videos regularly on the YouTube